This is Gene, and we're going to talk about data fusion on CPUs, or distributed data fusion, in other words. Um, so let me just start with some motivation. So here's a bunch of database products, right? And they're on a spectrum from like off the shelf, ready to go, to write your own database. And as we saw in the first presentation, data fusion is in this special spot where it's a library that gives you all the things you need to build a database. You don't have to go out of your way to implement everything from scratch. Um, so why do we like data fusion? Performance and extensibility, right? That's kind of the bread and butter here. And a big reason for why the performance is good is because of the execution model. For example, we use arrow kernels, it's pull-based. You use partitions as a unit of parallelism, which map very closely to the number of cores on the machine. And we have this like async Tokyo runtime on top of this like thread per core architecture. So data fusion is super good at squeezing performance out of the cores that you have available on your machine. But what are some problems you may encounter? As time goes on, data sizes, they increase, but your latency expectations kind of stay the same. Maybe you could query like 100 gigs in some amount of seconds, and tomorrow you need to query 1 terabyte in the same amount of seconds. So what do you do? Well, you start by vertically scaling. Cores are the unit of parallelism pretty much. You throw more cores at the problem, but you may find that you run into other bottlenecks like memory or I/O or downloading things from object storage and whatnot. So this leads to the idea of what if I just had a bunch of machines, and each of these have their own cores and other resources, and I could kind of transparently take a data fusion query and then just run it across these cores and take advantage of all this parallelism and meet my same latency expectations as the single node use case. And that's kind of the inspiration behind distributed data fusion. So firstly, we're a library. It's distributed primitives for data fusion. It's not an out-of-the-box product. And we use the same execution model, and we aim to achieve linear scaling with the number of cores. We're also unopinionated and extensible, and we're more or less trying to be as close to single node data fusion as possible, taking the same plans, using the same features, and running them in a distributed environment. So now I'm going to hand it off to Gene, who's going to talk about exactly how we do that.
Yeah, so as Jay mentioned, we're trying to stay as close to single node data fusion as we can. So that's what we'll start here with this query. So here we have a simple aggregation query over some arbitrary weather data, and we'll build our single node data fusion physical plan, starting with selecting or scanning some data from our weather table. We are doing an aggregation. Count star is our expression. So we do this aggregation pipeline on the rain today column, and then finally a projection of the rain today column and the aggregation that we did. So taking this plan, we want to distribute our queries using network plan operators that we implement in distributed data fusion as just implementations of the execution plan in single node data fusion. This is the shuffle, coalesce, and broadcast. Then we apply some custom optimizer rules to get our distributed plan. And we also have some distributed configuration options. And, oh, wow, it's going fast. Something important to note and just hammer home is that this is all provided by DataFusion's extensibility. So we're trying to be as unopinionated as we can be and use DataFusion's primitives to create this distributed library. So as I mentioned before, distributed data fusion is kind of just one big physical optimizer rule with a few steps in there. So first, we'll add a final coalesce. We will then annotate our plan, estimating any tasks and network boundaries. And then finally, we'll materialize our distributed plan. So I'll go into that now. And the first step here is adding a final coalesce. So As you can see at the top of our physical plan, we have multiple output partitions. And because we need all of our data to end up on a single task or worker at the end of our query, we'll insert a coalesce partitions to ensure that all of our data gets onto a final worker for the results. Now, we get into annotating our plan, which is the bulk of the logic here. So this is a bottom-up traversal starting at the scan, and we estimate that this scan over 16 files is going to take 4 machines, and we annotate it as a plan node or just a normal physical plan node. We then walk up the plan, and we inherit the 4 tasks from the operator below, and also annotate this as just a normal physical plan operator. And then when we get to a repartition, this is where it gets a little interesting. So we do the same thing as expected, but since we're shuffling data, we insert a network boundary marker here tagged as a shuffle type, and we estimate that after the repartition that this will take 2 machines or tasks to process this. And now continuing up our plan, we compute the aggregation, which inherits the tasks below. Same thing for the projection. And then coalesce will be another one of these network boundaries here. So we insert our network boundary with the final task marked as a coalesce, and then add our final node on top. So this is our final annotated plan, and now we just need to materialize it. So we do another bottom-up traversal. Because we have 4 tasks, we copy the operator 4 times. Then we add our own operator here called the partition isolator, and this ensures that each machine only sees the subset of data that it's responsible for computing. We then walk up the plan. We insert our aggregation, our repartition, and when we hit a network boundary, we encapsulate all the operators below in what's called a stage, and then each subset in its task, which is synonymous with a machine. We then insert our network boundary operator, which in this case we have marked as a shuffle that receives data from over the network from the stage below. And then we continue to build the next stage. So we insert the next normal physical operators on top and form the next stage until we get to the next network boundary above, which is a coalesce. And then we insert our final stage there. So now we have our final distributed physical plan here. And to show the difference, this is the original query in single node DataFusion. This is the physical plan that it gives us. And then this is what the full distributed plan that we just built step by step looks like at the end. So that is the full process of planning a query.
Thanks. All right, so I'm just going to show kind of like physically what happens now that you've all seen the plans. So here's like a machine. It has some process running DataFusion. You have a query that comes in. That's the substrate symbol, just like a logical plan you can imagine. And in our scenario, what you would do is spin up like a cluster of these workers that can communicate with each other in this like n-squared fashion. They're all connected to each other. And each one of these is able to serve queries. So what happens first is that if a query comes into a worker, that one is responsible for the planning. So here we do DataFusion's like logical and physical planning, run the distributed optimizer rule and worker assignment. I also wanted to point out that like this is a big extension point for distributed DataFusion. Like you can imagine that we need to decide how many workers a query should run in. That's something you can actually implement as a user. We have a trait for that. And worker discovery as well. There's a trait for that that you can implement. So you have full control there. So this worker does the planning and then execution starts. The execution model is exactly the same. So the only bullet point I have there is that we used arrow flight to send the record batches across the network. It's a pretty natural thing to use for arrow data, which is backing data fusion because it's flight is like built on top of gRPC and it's meant to like zero copy arrow onto the network. So execution starts from the bottommost stage, which had 4 tasks. So here we decided to split it up into to use all 4 workers to execute it. And then the next thing that would happen is like the shuffle, which is above this stage, streaming data to the 2 tasks in the stage above. So here are those 2 tasks, which were randomly chosen by our default implementation of the worker assignment. And then these 2 are streaming results back up to the coordinator for the final coalesce right here. And then the coordinator is just streaming arrow back to the user. So we have some benchmarks. These are admittedly a little bit apples to oranges. Like we're comparing distributed data fusion with like Spark, for example. I think it highlights the trade-offs very well. Spark is meant to be like a very fault-tolerant thing that materializes things to disk. Here, we're explicitly trading off that in data fusion for better latency. The thing that we're probably most comparable to is Trino, although there's many differences. But you can see, like numbers-wise, we are able to compete with Trino. So this is TPCH scale factor 1, and here's 10. And there's actually a link to this in our repo, and we actually have instructions on how to reproduce it as well if you would like. So final ideas. So we had this at the beginning of the presentation, and if we were to add one more dimension to it, you can kind of reorganize these projects in this way. And what we saw before is that there's kind of single node projects like Postgres, and then there was eventually a need for like distributed Postgres as people wanted to scale their queries with the size of data that is forever growing. And then you can imagine that there's kind of the same need on this side that we're seeing, where we want to take data fusion, which is like super awesome, and distribute it in some way. Yeah, so what's next? The project is pretty early in its life cycle, so there's a lot of new things in flight, namely consistent routing, adaptive query execution, and making dynamic filtering work in a distributed environment is something that we're actively working on. And yeah, you're all invited to contribute. Here's the link to the repo. We have this fiddle, which actually lets you run example queries in your browser, and you can like see what plans you can generate. And then a link to the Discord. We actually use the Apache Arrow Discord, and there's a DataFusion distributed channel. So feel free to reach out there whenever you'd like. Sure.
Sorry, on my tabs.
Yeah. Do you want to go?
Yeah.
Okay.
Yeah.
Okay.
But we'll share the slides, so the link will be in there.
And yeah, that's all we have. And we can take any questions. Yeah. You want to take?
Yeah. Well, we'll see.
Pretty simple questions. How do you shuffle data?
There was a group by key. Yeah. So basically how it's planned, so say you're like in this example, I can go back. So the original query was we're grouping on the rain today column. So single node data fusion will actually, this repartition will be a hash repartition on the rain today column. And then when we plan here, we go to our distributed plan. These are all going to be hash partitioned on the rain today column, and then the network shuffle here correctly coordinates getting it to the right machine. So it's native with the repartition, how we get that. No, like if you had a partitioned hash join and you need to repartition. So actually how the planning logic works is when we get this original query here and we do the bottom up scan, anytime we see a hash repartition like this, so anytime that single node data fusion planned that it needed to insert a hash repartitioning, we'll have to shuffle our data. Sorry, I'm confused. Wait. So if we have a hot partition, how are we handling that? You said if we have data skew or sort order, what is the question exactly? Yeah, so we're not changing the planning that DataFusion's doing up front in distributed DataFusion. So if that shape happens in the single node plan, then it would be mirrored here and is something that yeah, we're not handling right now. Maybe anyone else?
I can just add one small thing. I think well, data fusion, if you're sorted on the grouping key, it'll try to do a streaming aggregation. So it would actually not even include the repartition. And then in distributed data fusion, we would avoid the network shuffle. That's something we actually see a lot in our use cases. Yeah. Mm. Yeah. Yeah.
We don't have any official benchmarks, but I have run it on scale factor 50 or 100, and still see good scaling with it. Yeah.
Yeah. I actually did that, and yes, we run it with scale factor 100. I would really like to have put those benchmarks as the base thing that we expose. Unfortunately, all the other engines just crash on that scale factor for the 4 specific machines in which we are running. So no comparison. I mean that's a benchmark, yeah, but it will be a very boring graph, so it's not there.
Oh, okay.
Locally, there's no way by not sending data and merging with larger than here. It can happen that work that suddenly do you think it's across nodes that can be quite expensive, more expensive than the actual operation?
You want to take this one?
Do you consider that?
Yeah, that's something that we're actively working on. Yeah, yeah. For example, for adaptive query execution, Gabriel has been working on maybe reducing the number of tasks in the next stage, if that makes sense. And we also, people are contributing to stats even in core data fusion, which will help with that as well. Yeah. All right. Cool. Thank you.